Okay, okay. Hello, everyone. It is my great pleasure to welcome and introduce our speaker for today in Raising a Mathematician Training Program 2020. We have a very special guest. His name is Damjan Kobal, uh, and he's from University of uh, Ljubljana in Slovenia. And let me just give you a quick background of his. He's a major in mathematics. He did his PhD in mathematics, and he could have continued research in mathematics, but I mean, of course, he is doing research in mathematics, but he turned his attention mainly towards teacher training and education. And he is an amazing teacher. What he does in his University of Ljubljana is that he trains teachers on different areas in mathematics. So he has dedicated himself to the work of creating good teachers for the society for the future. And what he does is, we met at one conference. There was an international math conference named IMER, Association of Institute of Mathematics Research, Education and Research. And we met there, and that is where I saw his presentation. And he keeps visiting a lot of conferences like I guess some of you would have heard about ICME. So like ICME, there is, I mean, ICM, International Congress of Mathematics. There is another such conference that happens on mathematics education, which is called ICME, International Congress for Mathematics Education, where math educators from all over the world, they come together, they present papers, they share ideas. So he regularly visits ICME, and ICME also happens once in 4 years, if I'm correct. And he has presented a lot of papers in such conferences, and especially students in batch D of RAMTP. I mean, there is something that I just wanted to share with you. There is a publication named Challenges. I mean, the title is Challenges and Strategies in Teaching Linear Algebra, and this is a compilation of all the research articles of ICMA 13. Am I correct, Damjan?
Just regarding linear algebra.
Just regarding linear algebra, yeah, correct. So why I'm stating this is because our batch D students, they discuss linear algebra in great detail, so it might be of interest to them. So you have Damjan's, the name is DA. You can see on the top left corner of the screen, Damjan Kobal, and you can just Google Damjan Kobal mathematics, and you will get all the links of his of his work. And if you go to his university website, you will see the links of his publications, and you can have a look at some of the articles you might find on ResearchGate and all that. So he takes interest in introducing all these all these ideas in mathematics in much interesting ways for the modern day classrooms. And he also does a lot of sessions on using technology for math education, but he's very critical about it. He's not a big fan of doing anything and everything with technology, but using it wisely and carefully. So I welcome you, Damjan, for this session. And,
Thank you very much.
And over to you. So what we will do is we'll just whatever questions you might have, students. What I would urge you to do is just type the questions in the chat box, but see to it that the question is pertaining to what is being discussed right now. If it is not pertaining to something that is being discussed right now, you can hold on to the question till the end of the session. We'll try to address it during the question and answer session. And as we had discussed in some other sessions in the past, try to avoid chat, try to avoid talking or chatting with each other. If somebody is asking a question, somebody else doesn't have to take the responsibility to answer that question, because it will just spam the chat. Okay, you can type your answer if there is any question that Damjan is asking, and then I might just jump in to put up any question or something like that. So let's start the session. Thank you so much, Damjan.
Okay,
Please
thank
go
you,
ahead.
Vinay, for this nice introduction. You said a lot. I don't know what else could I add. Maybe for introduction, hello everybody. It's a great honor and a privilege to talk to so many young students from all over India. I'm really, first of all, a teacher, and I might want to start with a quote of not a teacher but a businessman. And you probably have not heard of him, or maybe you have. And I will ask you, can you see the screen which I'm showing you?
Yes, we can.
So can you see the quote? And have you heard about Lee Iacocca? He's one of the most famous businessmen, maybe of all times, of the United States of America. He was a director of General Motors, Chrysler, and that's what he said about teaching. He said, in a completely rational society, the best of us would aspire to be teachers, and the rest of us would have to settle for something less, because passing civilization along from one generation to the next ought to be the highest honor and highest responsibility anyone could have. I don't know, I wish that many of you smart young people someday would not only aspire to be great engineers, great scientists, but also to be great teachers, to teach and pass on these ideas of civilization, to learn to be smart. You know, in mathematics is so symbolically describes the essence and the core of what it means to be smart, to be good, to be rational. It's all about understanding what is the cause and what is the reason of all that is good and all that is bad. Mathematics could really and should really be something that teaches us how to be simple and how to understand the complexity of life. And if you see at the back this initial animation that I put on, I will talk about conics. And you can say a lot about conics, about conic sections. And I'm sure in one or another way you have heard about conics. The simplest of all conics is a circle, or an ellipse, or a parabola, or a hyperbola. These are already complex ideas or terms in mathematics, but basically they come from such a simple laws of nature, or if you want, laws of God, laws that are inscribed within the nature, within our life. And understanding this simplicity, understanding the power of simplicity that mathematics offers, gives you really an inspiration of how to look at life otherwise. So I guess you can see here in this animation, it's just a bunch of lines, right? And they are just moving around and they are forming these shapes of ellipse. And then the ellipse is transforming, it's becoming a circle, and then it's becoming a hyperbola. And what is going on? It seems like a mystery, but it's not a mystery, it's just a simplicity of some very basic ideas. And I will go back and start and assume, oh, okay, just one more thing. I was going to tell you also just a word about Vinay before described me as being a mathematician, being a teacher. I was going to use just a minute to tell you where I come from. I'm sure you can see the big map of a part of Asia and part of Europe, and you see India. And if you go up to the left corner of your screen, you would see Austria up here and Hungary, and it's Italy here on the left, just on the very edge of your screen. I'm not gonna move around maybe just make it a little bit smaller. And this small little tiny country up here is Slovenia. If I move it more to the center, now you can see Slovenia, and that's where I come from. If I zoom in, this is the capital of Slovenia, and I live up here very close to Ljubljana, and just for fun of it and for the joke, and to show you a little bit about what mathematics is all about. It's about technology that is behind. What I'm showing you now is just the smart use of technology, and none of this technology could be done without very basic mathematics. And this is my house. And this is the school, a tiny little school in the village where my daughter goes. And this is the neighbor's goat's farm, because we live really in a countryside. And if I just move on and show you, well, maybe not. Let's just move. This is my tiny little village, and now you can imagine if we just zoom all the way back, and just admire and see what the technology and what the smartness of human mind can do. We can communicate over half the world, and it's all about what a human brain can do. And let's go to the simplicity of mathematics. Let's go to the power of mathematics. I would assume that at least many of you, if not all of you, very well know the conic sections in a sense of parabola y equals x squared, or the circle x squared plus y squared equals r squared, an ellipse, which is just x squared divided by a squared plus y squared divided by b squared equals 1, and so on. And now I'm just reciting you this on purpose, because I'm sure you know and you understand and you remember as much as you do. This is analytical expression, which is very mathematical, very analytical. It uses coordinate system, right? X and Y are just the coordinate axes. These are based on Descartes' coordinate system. And in coordinate system, basically it all depends on understanding a distance, right? Coordinates X and Y, what do coordinates X and Y mean? Well, basically they just mean what's the distance from X axis and what's the distance from Y axis. But we can understand and look at these ideas also in another way. And now I'm going to show you something that is just a challenge for you, or you can do it back at home. And I'm going to switch a little bit the camera. Hopefully now you can see a piece of paper which I have in my hands, right? Yes, can you see that? You can see a piece of paper. And just imagine this piece of paper as being half a plane. And I will draw a point up here, a simple point. And I have a piece of paper, right? I'm not going to do this for half an hour because it would be a waste of time, but you can do that by yourself, or you can do it with your brothers or sisters or whatever. And now your task is...
Excuse me, Damjan.
Yes.
Can
Yes.
I just tell them, students, you can do pin video so that you can see it a little bigger. You can have a bigger image of Damjan of the video, and what you can do is you can drag the partition between the video and the presentation to the left so that you can see what he's going to present in a enlarged form. Try it and see if you get it. If you don't get it, don't spam the chat. It's okay. You just try to watch whatever you can from this. Okay. Thank you. Over
Thank
to you,
you.
Damjan.
And this would be just the idea. Even if you see it on a very small picture, if you just get the idea, you can just try it by yourself. And I'm just gonna to switch to computer animation to show you what I'm trying to show you. Now just imagine you fold many times this piece of paper in such a way that the edge of the paper touches the point or crosses the point. Can you see that? This would be one fold. And then you just do another fold. And each time you just take care that the edge of the paper crosses that point. And I'm sure you understand that you can do billion and zillion of these folds, right? Imagine, just do it for your homework and observe what happens with the piece of paper. And because today we are lazy and we are smart and we have technology, let's do this folding with a computer animation, okay? Hopefully this works. Can you see this is the edge, this line represents the edge of my paper, and this point represents a point which I drew, and the line could be any line. And now as I'm making these folds, I can just do them. You see, this would be one fold. I'm folding this point over to F, right? If F was here, just in, well, these points are now used with, they are chosen by a computer. But now let's just do many folds. Let's just do 300 folds in a second with a computer. What do you see? You see a parabola, right? Or let's say at least you see something which looks like a parabola. And this depends on the line, right? And depends on a point.
Excuse me, Damjan.
Yes.
Many of them might not be knowing what's a parabola.
Okay.
I mean, they might be completely new to the term and what it is. So if you would want to just state what it is.
Okay.
Uh,
Wonderful.
Conic sections,
Just
they're completely new to it, some of them, many of them in fact.
okay. Thank you. Thank you. Okay. Parabola, you see, let's just think about parabola as it's this weird shape. Okay. It's like a rounded bucket or something, which goes up to infinity. Yes. Now, this parabola was already known to the old Greeks, and it was totally geometric. Let's just think about parabola geometrically in such a way. Look, we have a line, we have a simple line, and we have a simple point. And now we try to think about points which are equidistant. So they are of the same distance from the line and from the point F. Take any point here down on the line. Take the segment between A and F. Take the perpendicular line to my line in point A. You see it's perpendicular to this line, original. And now, if you take a bisector of A to F, what do we get? Because this is a bisector of this segment A to F, point T is equidistant from the line and from point F, right? Why is that? Well, because this triangle is an isosceles triangle, right? Why is it isosceles? Well, because this is just a bisector of this segment, right? So from T to F, that's the same distance as it is from T to A. And because this is perpendicular line, this distance is basically the distance from point T to the line. You see, this was the geometric construction of a parabola, which was known already to Archimedes. Now just imagine, and we can do this with a computer, as you move this point A along the line, point T shows you the shape of a parabola. So what is a parabola? Well, intuitively, parabola is just a curve. It's a line on which this point T passes, right? While using a computer, we can also draw it. You see, this is a parabola. And parabola is basically, what's a parabola? These are all the points that are equidistant from a line and a given point. The closer this point is to the line, the narrower would be the parabola. You see it? But still, you see this triangle is an isosceles triangle, right? Yeah. Okay, let's just move on and see what wonderful consequences follow from this very simple geometry. Recall, we have a line, we have a point, yes? And we have a point on this line. We draw a segment from A to F. At this point, T is equidistant from line and from F, right? Now just recall, this was a bisector. This was perpendicular line. Okay. This bisector is a tangent of a parabola which we don't even know yet where it is. We just know that the parabola is a curve where point T moves. And this line is a tangent to that curve. Why? Why is a tangent? What does it mean to be a tangent? Tangent means that it only touches the curve in one point, right? So, because we already know that T is on a curve, it cannot just pass by the curve. So it's either a tangent or there is another point which would be on the curve. Could there be another point K on this line which is also on a parabola? Well, if there was such a point K, then this distance from K to A should be the same as distance from K to F. Sorry, this line from A to K is the same as distance from K to F, because this is still an isosceles triangle, right? But the distance from K to our line is the same as distance from K to C. And distance from K to C is not the same as distance from K to A. So obviously, this line must be a tangent, right? And now if you observe it, it's obvious, you know, this line is a tangent. Well, and now somebody who doesn't like or is not good in math would say, well, what's that good for? Well, yes, it is good for many things. Just look at this, what follows. Let's just go on. Recall again, this is a point F, which is called the focus of a parabola, right? This is a line which defines the parabola. And we know that this is a parabola. And now just observe these angles. The brown and the green angles are the same. Why? Because they are just opposite, right? And brown and violet, or whatever it is, blue, are the same because this is an isosceles triangle, correct? Therefore, the green angle is the same as the blue angle, correct? Okay, what's that good for? Just look what's good for. We know that any point on a parabola has a very, very special property. If a ray comes in a direction of which is perpendicular to this line, which would be the same as the, let's say, the axis of a parabola, it would just bounce off the parabola directly to the focus. Yes, you see the green angle is the same as the blue angle. Therefore, if you just imagine a ray coming from, let's just say that this line was horizontal, then the perpendicular line to this horizontal line would be just vertical, right? Okay, what do we know? You see, any ray coming down vertically would bounce off the parabola directly to the focus, right? This is highly non-trivial. But it follows from the very, very simple idea, which was known, as I said, already to Archimedes. Now let's just go into very intuitive interpretation of that. Imagine you have a billiard table, let's say such a table, which has a hole here in the focus, right? And now you try to shoot a ball so that it would bounce off directly to this hole, which is in the focus. How should we point this arrow to make the ball bounce off to the hole? What do we do? Well, if we understood well what I said before, there is only one and just one way to make the ball bounce off to the hole. The line should be totally horizontal. Yes? And it doesn't matter where you put it. If it's horizontal, it would bounce off directly to the focus. Do you see? And again, one could say, well, what's that good for? It's just for the fun of it. No, it's not just for the fun of it. It's great use of it. No satellite antenna would exist without that. No radar would exist without that. Just imagine how radar works. You see, depends on where the satellite is. You have to position your satellite antenna in a direction that a ray would bounce off directly to the sensor, which is put in the focus. And if we just imagine that we have like these rays coming from the satellite, you see, this is satellite dish which is not properly positioned. The rays bounce off not correctly, right? While this would be a satellite dish which is positioned in the right direction, so that all the rays would bounce off to the focus and to the sensor in the center. And even more, have you ever asked yourself how car lights work? Every car, there are millions and millions of cars around the globe today, and all have lights. How do lights work? How do long and dimmed headlights work? Well, basically you just switch, right? You switch the long headlight off and you turn the short dimmed light on. Yes, but how does it work? Do you see this works just by understanding the parabola. The light of a car, if we simplify it, it's just a parabola. Look, if the source of light is put in the focus, then any ray would just bounce off horizontally. If we do a simulation with a computer, you see, this is a long headlight. Yes, this is a long headlight. Okay, how do we make a short, how do we make a dimmed headlight? Well, very simple. We just move the source of light a little bit ahead of the focus. Well, this doesn't look like a short light, right? Well, what do we have to do? We have to dim the light underneath and send the rays just to the upward part of the parabola, and that's a short light. How is this realized? Just recall, the source of light is put a little bit ahead and it's shaded from underneath, right? Okay, you see, a long light, short light, and here you have a real picture of a car light bulb. Do you see there are two little wires inside? Here you have a scheme of it. Two little wires, just 1 or 2 millimeters in between. This one is put exactly in the focus. Yes, and when this light, when this wire makes the light, then you have a long light. This is this one. It's exactly in the focus. When you turn the long headlights off, this one goes off, this one goes off, and this one comes on, which is, it's, you know, it's covered underneath. It has this small little cap underneath. Yeah, it's a metal cap which would not let the light go downwards, but only upwards. And besides that, of course, if from this source light, the light would just go straight ahead, that would also make a long light. So you also have a hat underneath, you see, not underneath, in front, you see, it's covered from this side, so that the light could not go straight ahead and it cannot go downwards. It can only go upwards, and then it bounces off in such a way as you can see in this picture up here. Okay. Yes. So that's how we get this parabola, understanding how the parabola works, and also the big use of it. I mean, it's really a nice, and of course, if we talk about parabola, that's how our parabola was geometrically defined, right? Just the points which are equidistant from the line and a focus. Well, some of you might know that analytically, parabola is given by an equation y equals ax squared, and basically that's the same. Just you have to find the right proportions, the right a, which means how open and how where is the focus and where is the you know, now we would just need to play with this line and with focus to make analytical parabola exactly the same as geometric. But let's move on to some really nice intuitive aspects. Vinay, did you want to say something?
Yes, a student has asked, is the distance from the center of the parabola to the focus equal to the distance from the focus to the vertex?
Okay, so maybe it's the best to look back at this one, right? Oh yeah, I see it's even a question in chat, but I'm just focused on
Yeah, please, no problem.
Hopefully this comes on. So the question was whether it is the same distance from focus to the parabola as it is from parabola to the line, right?
The focus of the vertex, yeah.
Yeah.
Focus to the vertex, yeah.
If we remember back, wow, I don't know why this is not refreshing, but if we remember even our folding a paper, we can answer this question, right? Can you see the piece of paper?
Yes.
If we fold it straight like that, right? So that it would be parallel, this would be a tangent, right? And of course, it is exactly in the middle, correct? So yes, this distance is the same from the line to the parabola, which would be coming just down here to the focus, right? Gosh, why is this not working? Maybe I'll just need to reload it. I will just reload it. Hopefully it will work. Yeah. Do we see? If we fold this point, which is exactly below the F, the focus, of course, this fold is exactly in the middle, right? Correct? And it's obvious, even if we think about this point, which is exactly of the same distance to F and down to the line, that the answer is yes. Okay? Let's go to something else. Now let's take, before I took half a plane or I took a piece of paper, now I'm taking a piece of paper and a circle. Can you see it? Can you see the circle?
Yes.
And now imagine, as I drew a point before on half a plane, now I can draw a point somewhere within a circle. And these are some very nice, even philosophical questions if you want. You know, if you imagine that this circle is very big and that we are very small, basically there is no way for us with a human touch, sight, and everything that we have to distinguish between this picture and this picture. Because just imagine if the point is very close to the edge of the circle and we are very small, this line looks very much straight, right? And now if we would do the same thing as before, just now imagine we could even cut the circle out of the paper. It would be even nicer to do that. And then with that circle cut out, we would just make the folds so that the edge of the circle would end on this point. And now let's just go back to our computer simulation. Can you see it here? We have a circle with a center, and we have any point. Let's say it's here. And now we make a fold. First, we make one fold. We fold this point to F. Can you see? Folding this point to F basically means just making a bisector of the segment, right? Now let's just do many folds. Wow, what a nice shape. Can you see what a nice shape? Well, this shape is called an ellipse. And it's very much related to the idea of what a parabola is. Now, because we have a computer and we can just do this dynamically, you can see how this ellipse changes. You see, if the focus, if this point F would be in the center, what do we get? Well, we get a circle, which is just half the size of the original one, right? If it's close to the edge, the closest it is to the edge, the tinier is this ellipse, right? Wow. For some of you, what does it mean? What is an ellipse? Ellipse is something that is also quite simple. It can be defined in such a way as a circle. What is a circle? Circle is just all the points that are equidistant from a center, right? Well, what about if you have 2 points and then you take a rope of certain size and you just try to reach it as far away as you can. Just imagine you take the 2 points and then you take a fixed line, a fixed rope, and then you push this pencil to the very edge and draw what you can draw. You see the line, the length of the 2 lines is constant. Yeah, it's like a constant rope that you go around, and what you get is an ellipse. And you see, this ellipse is something, again, that is very simple. It's defined by all the points for which the sum of the distance from one point plus the distance from the other point is constant. You see, the length of these 2 red lines is the same wherever around you go. Yeah, that's constant. And something very interesting happens. It's quite similar to what happened before with the parabola. Just you have to understand it properly. Now, if you would take a ball and put it in one of those 2 points, we can call it focus again, one of the 2 focuses. We put it here, and which direction would you need to hit the ball so that it would bounce off to the other point? It's just amazing. You can just hit it any direction. Doesn't matter where you hit it. It would always bounce off to the other one, right? Now, if we go to this folding ellipse, it's pretty straightforward to understand and see why this shape, which is basically just in mathematics, we call this an envelope. It's just like, you know, what you would get if you do this with folding the paper. Just take a circle, cut it out with the scissors, make a point, and then make 100 folds so that the edge of the circle would end in this point F. And what you would get something like that. You would get a nice ellipse. But let's now just go back and try to understand this. Let's just make one single fold from this one point, okay? And again, do you remember before in a parabola we said, again, this red line is just a bisector from the red point to this F, correct? And now let's look at this picture. It's very, very similar to the picture which we had before with the parabola. Look, this red point just travels around the circle, right? This dotted line is perpendicular line to the circle. Basically, it just goes through the center of the circle, right? And the red line is a bisector of the segment from F to the red point. Therefore, this triangle is an isosceles triangle, correct? Therefore, a distance from F to this point is the same as a distance from this point to this point. Yes? Okay. So what's the distance from the center of the circle to the red point? That's constant, right? That's just the radius, correct? Okay, but then from O from the center to this point plus from this point to F is the same as from O to this point plus from this point to this point. Therefore, a distance from the red point to O is the same plus a distance from red point to F is constant. And that's just a definition of an ellipse, right? And that just tells you why this would be an ellipse. Now we can just go on and play forever. I think I have here, as I told you before, you can do that at home. Take a circle, cut it out from the paper, and make these folds. And you would get, from the folding of the paper, you would get this nice ellipse. Now, take a transparent paper. It could be just a baking paper or something. Make a circle. And now draw a point which is outside of the circle, not inside, but outside. And now do the same. Try to fold this, but the line of the edge of the circle would cover the point, and do 1000 folds, do 100 folds. Just keep doing that. Keep doing that for a while. What would you get? Well, we can do it here very easily. Just imagine this point is outside. And again, we would fold. We would do a lot of folds so that this F would end up on the circle, or that the edge of the circle would end up on point F. What do you think? What would we get? Let's just make a couple folds. This would be a fold which would make F end on this point, you see? And do one more, do one more, do one more, do one more. Ooh, wow. You get a hyperbola. Look, the same hyperbola, just whoops, it's an ellipse. It's a hyperbola, it's an ellipse. What's the definition of a hyperbola? Well, this is for your homework, but you can realize that again, you get very, very similar thinking as before. This now is again an isosceles triangle. Just now you would figure out what? Again, this distance from a center to here is constant. So a distance from red point to this red point minus from this point to F is constant. And if you take absolute value, you can take also this point to be on the outside. Yeah, we'll see this in a moment. So this point could be also I don't think, yeah, I have it here. You see, like, see what happens? Look, observe now what happens. Whoops, and it's on the other side. It's just amazing. What a beauty, what a deep meaning comes from a very, very simple mathematical ideas. Okay, and the time is short, so I will just go on and tell you two very brief ideas. These are not ideas to understand and to give you proofs, just to give you ideas to think. And you're smart, and you will be able to do a lot of this thinking. And if I am able to, I will show you the link where you can see all these animations, or if not, you could just get them afterwards. This would be an idea which I'm gonna tell you in a minute. Why parabola, ellipse, hyperbola are called conics, conic sections. Because if you take a cone Can you now see here the idea of a cone? It tries to be a 3D. Can you see it? Try to visualize it by this line, how it's moving around, and it's kind of describing or how to say, drawing this cone, this infinite cone. Okay. Now just imagine that you intersect this cone with a plane. Can you see the plane which I'm moving up and down? And if you intersect this infinite cone with the plane, you get an ellipse, right? That's why the ellipse, parabola, and hyperbola are called conic sections. This is an ellipse. If I would put it in such a way, it would become a parabola, you see? And if I go to the other way, now I cannot really do it because the computer animation is kind of limited because it's really hard to imagine all this. But just to imagine why and how easy it is to see that this is really an ellipse. Just imagine, do you see down here a sphere, a ball which you put inside this cone? And this sphere is touched by this plane in this point F1. And then on the top, you put another sphere. Can you see it? The green one. And the green sphere touches this plane, this blue plane, which gives you an ellipse in point F2. And these two are the two focuses of ellipse. Why, for the God's sake, this would really be an ellipse? Proof is just incredibly simple. It's just amazingly simple. Just imagine now, can you see how I travel with this red point around what could be or what would like to be an ellipse? Can you see it? And the distance from this point down to my point and even down to the other point where the small little circle touches the cone, this is constant, right? Because this just moves around, and it's of the same distance, you see? And from this point up to this point is the same distance as it is from this point to the F2. Why? Because these two lines are just the tangents to the upper green sphere. And why these two blue lines are of the same distance, are of the same length? Because these two blue lines are again just the tangents to the small little sphere down. So a distance from this point to F1 is the same as distance from this point down to this circle. A distance from this point to F2 is the same as distance from this point up to the second parallel circle somehow. As this point moves around the ellipse, this line from up here down here is constant. It doesn't change. You see, so this is really, it's exactly an ellipse. That's just an idea. You can wonder and think on about it. There are plenty other things that I would like to tell you, but probably we are almost running out of time. Another aspect or idea, just for last couple of minutes. Just imagine you have 2 points, A and B, and all points P, for which distance from A to P and from B to P is 1. What's that? That's just a bisector, right? Yes? Well, what about if this 1 was not 1, but was something different, was constant, which was different from 1? Then it's so amazing, because this becomes an Apollonius circle. What does that mean, do you see? If you take the ratio, you see the point, this point, the red point, all the points on this circle are in the same ratio distance, AP from P to B. It's 192 in this case. I can take anything. If I go to the other side, it would be just circle on the other side. Yes? It goes all the way to 0 and goes all the way to infinity. Yeah? When it's 1, it's in the middle. Why is this good for? It's just that this is really a circle, Apollonius circle. This is a nice geometrical proof, which you basically have here and you can study later on. But I would rather show you just this very last idea of conic sections, which is just incredible. Imagine and recall before we said what was a parabola. If you take a line and you take a point F and you just observe all the points which are equidistant from this line to the focus, what do you get? You get a parabola, right? Yes? Well, now just look at this amazing thing. What about if you take a line and you take a point and you take all the points which are in ratio, I don't know, 1.5, 1 point whatever, 1.3 to the line, comparing a distance from P to line and comparing a distance from P to F. And all these points which are in this ratio form what? Yeah, look, these are all the points. What do you think? What do you get? Well, you get an ellipse. You see? What happens if this ratio is, if it's 1, it's parabola. If it's bigger than 1, it's an ellipse. What about if it's smaller than 1? You see, it's hyperbola. It comes from the other side. Basically, the story of conics is the story about understanding a very basic, very simple, incredibly simple ideas of distance. Basically, just a distance between, recall, just we observe just a distance between point, point, point line, well, point circle. There is much more, much more that could be studied and you could go in, but I hope you can see this very simple, very intuitive, very nice basic ideas. And once more, being a mathematician, it's not about being smart, it's about how to use your smartness to be modest and to see what all comes from the simplicity of very basic, very nice, very easy, very simple ideas. And yes, thank you, Armand. Simple and beautiful. I will stop here and I will just ask for a couple minutes break just to run for the bathroom, and maybe we can collect some questions in the meantime and answer some questions or have some discussion. Is that okay?
Sure.
We take
we'll collect questions till then. Yes.
Okay, just about 3 minutes. Is that fine?
Sure. Yeah. Okay. Absolutely.
Thanks.
Students, the session will be on. We have a question and answer session now. It will go on at the most up to 3:30. So if you have any specific questions regarding this, you can put your hand up and I'll quickly listen to your question, and then you know, so we can save time. Yes, Vishnu, what's your question?
Uh, how does the properties of ellipse explain the elliptical orbits of planets?
Okay, so hold on to this. I'll unmute you when he comes back. Okay. Arman, what's your question?
Sir, I have messaged it to you. You can.
Can you just repeat it for me?
Yeah. Is there some research done on 3-degree equations? Means categorizing them, like 2-degree are categorized as conics, so 3-degree as something else.
Okay, fine. I'll unmute you and then you can ask this question.
Yes, sir.
Yes, Soham.
Atul is there.
Soham. अच्छा question है?
I'll just ask to in what way that parabola, ellipse, and hyperbola, that we connect with these 2 points to have something different in a way that we have to go with the help of this GeoGebra.
Okay. I'll unmute you in some time. Yes, Imran.
Hello, sir. Am I audible?
Yes.
Sir, my question was that I have two questions, very small questions. My first question was, we got so many beautiful patterns, right? Sir, what my question was that, where is this patterns? Like, where can you apply this? Can you apply it in programming or in physics?
Okay.
And also my second question is that now we did for only 2D and we got a 3D shape. Like the 3D extra lines means that was looking like a 3D background. My question is that if we take, instead of the parabola, you take a 3D parabola, like something which looks like 3D, and then you do this fold, then will you get a 4D shape?
Okay, that's a good question. I'll unmute you in some time. Okay.
Thank you, sir.
Shreyan, how many questions?
1.
Okay. What is that?
Sir, in all the examples you are given, you are taking a line, right? You're taking the line for the first point, right? So what if instead of a line, we put some other shape?
Okay. So I'll unmute you in
like a sine wave or something.
Yeah, I'll unmute you in some time. Aman, what's your question?
Sir, my question is that what is the relation between the foci of an ellipse?
What is the relation between what?
The 2 points, like the focuses of an ellipse. Is there an interrelation between those 2 points?
You can just take any 2 points.
Okay, sir.
Yeah. Can you lower your hand? Nivesh, what's your question, Nivesh? Can you unmute yourself and speak? Nivesh, can you unmute yourself and speak? Neelam, if you have a question, please raise your hand. Nivesh, I can't hear you. Shravan, you have a question?
Sir, we saw many patterns of this conics. So, like, what is their application in real life?
Application of what?
Application of conics, like any of these patterns.
I think in the beginning, beginning of the talk, he explained quite a few applications, right? About radars and headlights. Were you there at that time?
Yeah, other than I was there only at the time of headlights.
Okay, before that also, so you had some connectivity issues, is it?
Yeah.
Okay, so you can watch the recording later, that part, and you'll understand. Okay.
Yeah.
I'm back.
Can you lower your hand, Shravan? Yes, so we have a few questions. I'll unmute them one by one. Yes, Imran. Imran, you can switch on your video while you speak so that Damjan can see you.
Hello,
Yes.
sir.
Hello, hello, Mohammed.
Hello, sir. Sir, my doubt was where can we apply the where can we apply what we have done so far? Like all these patterns which we found, where do you think we can apply?
Well, you see, one thing is I told you in car technology, no car light would function today without this parabola idea. No satellite would function without it. No satellite dish, no radar, no airplanes. This is just a few, you know. In science, in astronomy, all the radio and basically all the sensors which are used in astronomy would not function without these ideas of a parabola. But even, you know, if we go back, just being amazed at what these shapes give you, you know, it's not only about applicability. Yes, it is also about applicability, but it's even more about the beauty, you know, just to see what shapes, what the beauty comes out of these very simple ideas. Okay.
Okay, sir. And I had one more question. Sir, what we did was we took points, we took two-dimensional shapes, and then we got a background looking like a 3D.
Okay.
So imagine instead of 2D, why can't, if we take 3D, will we get a 4D background?
Well,
like when we take 3D shapes.
You know,
and you do the folds.
You know what folds, what would fold mean in 3D? That's even a question, you know. Folds are very much related and defined in 2D. That there is no, you know, maybe there are very many ways how you would define a fold in 3D. You know, that's a question. And what you said before, that we get from these 2D ideas that we switch and go to 3D to get the connection. That's basically where the name comes from. You know, this is what already the Greeks observed, this idea, how just by cutting these 3D shapes, you know, you get these 2D shapes, so to speak. And that was always a very interesting question, you know, like just if you have a circle and you just cut it, you cannot get anything but if you get a sphere, right? If you have a multi-dimensional circle, you cut it, you get still a circle. And this is just now a connection, how you see and how you understand. And even what I told you at the end, you know, that the parabola, hyperbola, and ellipse can be obtained as the proper ratio of distances from a point to a line. Also, that can be explained in 3D. The line, this directrix, is just the intersection between the two planes, one which is defining the circle, where one of those circles was touching the cone, and the plane which cut the ellipse out of the cone. And it's just amazing, you know, how these 2D ideas connect to the 3D ideas. And of course, you can go from 3 to 4, but it's you know, we have no imagination in 4 anymore, so it's probably not really the very beautiful idea from 2 to 3 cannot be applied from 3 to 4, because the most beautiful part from 3 to 2 and from 2 to 3 is that we can get this different perspective of imagination, while of course we cannot say that between 3 and 4, right? 4 becomes abstract, and analogies which we have from 2 to 3 we use to understand and comprehend what happens from 3 to 4 and higher dimensions in mathematics. Okay?
Okay, sir. Thank you, sir.
Thank you.
Can you put yourself on mute, Imran? and lower your hand. Shreyan has lowered his hand. Arman. Yes, Arman. Arman?
Yes, sir. Yeah.
Yes, you had a question.
Hello, sir.
Yeah.
Hello. Hello, Arman.
So I had a question that we categorize 2-degree equations as within the conics. How can we categorize 3-degree equations?
Oh, it's becoming quite complicated. Can you see the screen?
Yeah.
Yeah. You know, if I had 4 hours, then I would be telling you about that. For example, here you have what you see is just we have a circle, right?
Yeah.
And we have a point. Okay.
Yes, sir.
And we analyze all the points that are equidistant from the two, correct?
Yes.
Yeah.
Yeah.
And if we go out, we get the hyperbola, right?
Yes.
Remember before, well, what would happen if we take, like if we would analyze points which are equidistant from a line and a circle? That would get, basically we would get the same. Why? Because you see, if you analyze which points are equidistant from a line as from a circle,
They are the same.
that's basically the same as just observe what happens.
Yeah.
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 You see, but this is, again, this is the beauty of mathematics, you know, how you simplify, how one problem is transformed to the other, right?
Yes.
Okay. You get nothing new. You get nothing new here. What about if you consider equidistant points from two circles?
Again, the same.
You see, basically you get the same, right?
Yeah.
Now it's a little bit more complicated because you can go also to the other sides, you know, because now you could even observe, you could go the other way. You know what I mean? You see here?
No.
I'll observe this one.
Yeah. Yes.
You see? This one goes over to the other edge of the circle.
Yes.
And this one is different from this one.
Yes.
Yeah?
Yeah.
And you see, you get two hyperbolas. But you see, you still remain in the same order, right?
Right.
Well, then, oh gosh, no, I didn't show the right. I was going to show you another one, where if you would consider, oh, I don't have it prepared. I don't know if it works now. Maybe it's this one. Yeah, I think it's this one. If it will not get stuck again. Yeah, this is it. So remember, now we described here. You see, we have a circle, and we have a point. Yeah.
Yes.
And we observe the points which are equidistant. You see, distance from a circle to point P, ratio distance from F to point P is 1. What do we get? We get an ellipse, right?
Right.
Well, now what happens if, as before, remember, if we had a line and a point, and we switch this ratio to something else, we got an ellipse. Look what happens now.
Yes.
It's amazing. And this is of the 4th degree. This is a curve of the 4th degree, but it's still, look how beautiful it is. Basically, you get very much egg shape here.
Yeah.
It's quite amazing, you know, this shape. And, you know, if you go, it's quite obvious intuitively that if I go with this lambda, with this ratio to the other side, that you would get a symmetric picture.
Yeah.
And these
I
are
GeoGebra and found that these two curves are actually not independent of each other. Means we cannot represent them independently. The one egg-shaped and the one leaf-shaped one. That red.
what do you mean that we cannot represent them independently?
Means we have two. That 4-degree curve is comprised of an egg-shaped curve and a leaf-shaped curve. You can observe it over there.
Well, it's just, you know, you can, GeoGebra is very smart. You can do a lot of things just by implicit curves. You will probably need to learn a little bit more about even parametrically given curves, and you can do anything basically. I mean, it's really amazing what you can do. Well, in this presentation, this GeoGebra, this is just given as an implicit equation, as an implicit curve. Yeah.
Yeah.
Was that partially at least an answer to your question?
Yes, it did.
Yeah, you know, even the 3rd degree, the 4th degree, it becomes very complex, very beautiful, but it's not that simple anymore. You just get so many new options.
Yes.
Yeah. Okay.
Yeah.
Wonderful. Thank you for your question, Aman.
Yes, sir.
Next, Atul. So we have Atul, and you might remember Atul from the IMER conference, Damjan.
Oh.
Atul Dev. Yeah.
Great. Hello.
Hello.
Hello. Oh, hi.
Hi, Damjan.
Hi. Hello.
Nice to see you. Nice to see you.
Nice to see you again.
Yeah. My question is that, like, when we are talking about foci and when we are talking about directrix, can we put parabola, ellipse as well as hyperbola in one part? Because with that 2 points only, you have shown us that how the parabolic structure, how the hyperbolic structure, and how the elliptical structures that we are able to draw. So can we go ahead with this part with eccentricity and lattice rectum also?
I'm not sure if I understood you correctly, but you know, if you just take a directrix, the line and the point, that's the most universal definition of the conics. Because you get the parabola, you get ellipse, and you get a hyperbola with one single, you know, basically it's just the ratio of the points, right? Which is either 1, that is parabola, that's just a theoretical border between ellipse and hyperbola. Basically, I like to say that parabola does not exist. Parabola is just a theoretic line between ellipse and hyperbola, right?
Okay.
And if that's, as what I said there, as lambda, the ratio is 1, you get a parabola. If it's smaller than 1, it's an ellipse. If it's higher than 1, it's a hyperbola.
Oh, okay.
Yes? Is that an answer to your question?
Hello.
Yeah, can you hear me?
I think.
Yeah, I understand.
Okay.
Okay.
Yes. Next is. Okay, we will take 3 more questions. Nivesh.
Sir,
yes.
Can
Nivesh.
you say an example of application of hyperbola? Can you explain an application of hyperbola with an example?
Well, I'm afraid not. But you know, hyperbola is just, maybe it's more like a philosophical or cosmology question. It very much relates to the theories of the universe, you know, elliptic, hyperbolic, parabolic geometry, which relates to the very, very sophisticated questions. But you know, if you think theoretically about hyperbola and ellipse, basically these two are the same, in a sense that you know, describing intuitively, I just imagine you have an ellipse which is defined by two focuses, right? Yeah. And now as you push one focus, let's say to the right, this ellipse is becoming ever more narrower, right? You push it on, and you push it all the way to the right. It's very intuitive. Pushing it all the way to the right means pushing it to infinity. You get what? You get a parabola, right? Okay. And now if you can imagine, well, now you pushed it to infinity. Now push it a little bit further from infinity. And intuitively, what does that mean? That it comes from the other side. Yes?
Mm.
And can you imagine now this ellipse which you pushed all the way to infinity and further on, and it came from the other side? Basically,
Okay.
it's like the two parts of the ellipse which come from the other side together. You know, it's just the beauty of it. I mean, applicability, you cannot really talk about applicability in this direct way, as you can with a parabola and with satellite dish and car lights, as I said. But you know, the very ideas which are, you know, hyperbola and ellipse, basically, in a way, it's very much about the same thing. If we could eliminate our perception, you know, our linear perception and that infinity, you know, even if you take geometry in higher levels, which is not Euclidean geometry, which is, you know, Euclidean geometry is just the idea of it. There is no plane, you know. By our senses, you cannot distinguish a plane from a sphere. Yeah, because if it's further on, you just don't know. You know, these are the cosmological questions of astronomy, if you want, in a very intuitive way. I don't know if that's partially at least answers, or at least modestly admits that it's hard to say really directly about applicability of hyperbola. But in very many aspects, you just get, you know, this idea where you have the difference between the two becomes important. It's not the sum of the two, but the difference between the two, and you get the, you know, even in hyperbolic geometry, you know, if you talk about sine, cosine, and then you talk about hyperbolic sine and hyperbolic cosine, it's a very simple geometric understanding where you compare the ideas of ellipse to a hyperbola, and basically they become just the two sides of the same thing. Okay.
Sir, and then if conic is related to a Fourier transform like that.
Okay. I
have heard about it, but I'm not sure about it. Fourier transform.
Well, Fourier transform, you know, that's a tough thing. Fourier transform is related much more to physics, to understanding of the harmonic and sine and cosine, or basically sine is the same as cosine, and Fourier transform is, I know a little bit about it, not much. You know, maybe even my son, who is in music, knows much more. It's so important, but I don't see the direct relation to the conic sections.
Thank you, sir. Thank you for answering.
Thank you.
Nimesh, can you put yourself on mute and lower your hands? Yes, Adityan.
Hello, sir. Can you hear me?
Hello.
Yes,
Yes. I can hear you.
Yeah. So Vinay sir had told that you conduct a lot of teacher training programs. So I would like to ask you about the challenges which you face while training teachers versus the challenges which you face while training students.
Oh wow! How much time do we have? This is almost a political. It's a political question, you know. Training teachers is a problem because the society is screwed up. You know, teachers are not valued. You know, basically, I hope at least some of smart kids listening today would dare and would have courage and would be smart enough to become teachers, because that's so much more important than grabbing money. You know, you can do so much more if you change 2 or 3 people than if you, I don't know, have BMW. What's that good about? And you know, training teachers is a problem because today, in today's society, at least in the West, being a teacher is not something that very many smart people are looking for, which is really unfortunate, and it's really a sign of greed of society. I hope in India you are in a better position, and it's really wonderful when you get to train young people who are smart, who are devoted. You know, to be a good teacher, you have to be, you have to be smart. You have to understand mathematics. You have to understand the subject, and you have to understand how much more complex it is to be, I don't know, a good teacher. I say math is hard, but it's much easier than life. You know what I mean? So to be a good teacher, you do need to be a smart person, smart in very many ways, not just smart in relation to equations and mathematics, but also smart in understanding the human feelings, the motivations, the fears, the ambitions, and all that. The main questions for challenges in educating teachers is motivating them, trying to raise them up, not frustrate them, because it's very often a problem that people who are probably not that capable of being very good math teachers would go to become teachers. You know what I mean? That's a big challenge, because then you have to say, well, you know, you don't need to be that smart. You really need to have the basic understanding, and you have to have a devotion. You have to try to understand and have to try to see the beauty. I would say much more to see the beauty, because if you are excited about what you are trying to say, if you see the beauty of it, and you try to share this idea, you know, this is just so nice. I don't know if I may say it's I think it's Bernard Shaw said that if you have an apple and if you want to share it with somebody, you either give that apple to the other one, or you have to split it and you only are left with half. But if you have an idea and you share the idea, you both have the idea. And that's really the beauty, you know, of teaching, of sharing the ideas. It's so much more than materialistic approach to, you know, profitability and usability of everything. I don't know if it's such a question. It's a question for long discussion, but I hope at least I gave an indication of what I think about this crucial and wide problems.
Yes, sir. Thank you, sir.
Thank you
so much. that was really beautiful. That was very touching as well.
Thank you.
One last question from Adia Aisha.
Hello, sir.
Hello, Adia.
So actually, this question is not related to conics. It's actually about, was there a particular time or a particular moment when you just actually started appreciating the beauty and the simplicity of mathematics? Because that is something I think we all are actually missing nowadays. The beauty, was there a particular moment where you just
it's such a nice and almost personal question. I would say I don't remember this moment as mathematics. I remember this moment as trying to understand and see the reason behind human suffering, behind human good and bad. You know, I remember being a very small kid before I went to school, my mom told me when I was going to have a test whether I would go to school or not, you know, because I was too young to have to go to school, but I could go to school if I passed the test, right? And my mom told me, now you can think about whether you want to do it well or not, because if you don't do it well, you would have another year for playing, you know, not going to school. And I said, you know, Mom, you know how much money I could make and how much I could help you if I go 1 year earlier to school. I would finish the school 1 year earlier, and in 1 year I could do so much more than play. You know, it was thinking about, you know, causes and reason. It was this eternal why. Why is that this way? Could it be the other way? Could it be better? What could I do to make it better? You know, and this made me, you know, think about understanding and how understanding is important. And I think there, you know, then back when I was a kid in Yugoslavia, in Slovenia, there was a communism, there was this political system which was quite oppressive, and mathematics was so clear and, you know, so pure, you know, so innocent. You know, there was no politically, you know, what is right, just politically right, but what was really right. And that really amazed me, you know, this beauty when you see these simple little laws, you know, which are just very basic, like, I don't know, so if I use the Bible, but you have the similar things, just love your fellow being as much as you would like them to love you. It's a simple law, and out of that you could just derive basically everything. And mathematics for me, it's just a modus vivendi, you know. It's like how you should just think back, you know, like, why is that really true? Or am I just imagining it is true because I'm selfish, because I'm greedy, because I'm stupid? Am I really smart enough to understand that? And mathematics just teaches you to go back, and be honest and to do the best you can do. You never know what's the best, but you try to do. You try to get, religiously speaking, trying to get as close to what God wants you to do, whatever that means symbolically, right? I don't know if that's partial, at least, the question.
That was the perfect answer. That was the perfect answer. Thank you so much.
Thank you. And best of luck to you.
Thank you.
Thank you so much, Damjan. I got requests from students to see if we can extend the session, but unfortunately, you know, like I told you that we have another session.
Okay, I perfectly understand.
I can see that how much they all loved your session. You can see their comments in the chat, and I'll just ask one of our students in the senior batch to extend our token of love and appreciation for your session. So Ashwath,
thank you. It was a great pleasure for me, an honor to speak to so many young, nice people, smart people, and I hope at least from some of you I can hear one day, and I expect only good things from such good people. So best of luck to you, and in one or another way, maybe there will be another chance to meet.
Definitely.
Thank you.
Ashwath? Yes. Do you want me to stop the video because I think your internet connection is a little low? I think we are not able to hear him, right?
Okay. No, I can't.
Hello.
Yeah. Okay. So okay. Ashwath, can you say something? Hello.
Hello.
Yeah.
Am I audible right now?
No. I'm sorry. I'm
thank
sorry.
you so much.
Yeah. You can do one thing, Ashwath. You can just type in, and because the audio is very poor. Okay. I'll just ask. Okay, Imran. Yes, Imran is again one of our youngest participants. So, Imran, would you like to extend the vote of thanks?
Yes, sir. So the session was very like amazing. Like it blew my brains off. So what happened was actually I wasn't expecting conics would be so interesting. I was just thinking that conics means like the area of a cone, the surface area, and that's it. But this topics have really blew out of my. I'm sorry, it has really blew my mind. Thank you very much, sir. It was a very amazing session.
Thank you. Thank you.
Thank you so much, Imran. Damjan, we'll try to collate some feedback and give it to you from the students' end. And I would like to ask all the students to start their video so that Damjan can just see all of you, see some of the future mathematicians and scientists.
Wow.
And whichever areas they would pursue.
Wow, amazing. Wonderful. Wow, hello everybody. So nice to see you. Wonderful. Wonderful. I'm looking a little bit on the side because I put you on a bigger screen so that I can see more of you. Thanks so much. Thanks.
Thank you. Thank you so much, Damjan. And I'm sure these guys would have seen a very different flavor of conic sections. And this is not generally how conics is introduced. And I'm sure this will give them a very different perspective and motivate them to pursue.
And I tell you, it's just a start. There is much more to it. So good luck.
So thank you so much, Damjan. Really appreciate your time that you took off for interacting with all these students and rubbing off your love, passion, and inspiration towards mathematics and teaching. So what you shared was not just mathematically inspiring, but it also touched all of our hearts. So we sincerely thank you for this wonderful presentation, Damjan. Thank you so much. Thank you.
Thank you.
Thank you.
Best of luck to you.
Bye-bye.
Bye-bye.
Thank you so much to you too. Bye.